In this video, we're going to look at rigid tank applications. Again, that's going to apply constant volume application because if the tank is rigid, there's going to be no boundary work, so the volume is not going to change. The boundary is going to remain fixed. And so if we look at our first law, heat transfer minus work done is going to be equal to change in internal energy plus change in kinetic energy, change in potential energy. Again, there's no flow, so there's no change in kinetic energy, and there's going to be no change in elevation, so no change in potential energy, so that's going to go away. And in most cases, the work is going to be zero, but there could be, like, say, a paddle wheel or something in here. We're probably not going to look at those applications in this video, but you could have that. So we'll leave the work in the equation. Uh, so we're going to end up with this on a per mass basis. Now, if we multiply through by the mass, we're going to end up with Q minus W is going to be the change in internal energy. So, for example, if we're in SI units, this would be kilojoules per kilogram, this equation. But then if we multiply it by the mass we have, we'll end up just with kilojoules all the way across here. So we're going to look at some of these problems. Let's take a look at this problem. A rigid tank has a volume of 1.2 meters cubed and contains water at 650 kPa with a quality of 0.7335. The tank is heated until there's only saturated vapor in the tank. What is the final pressure? How much heat was added to the tank? We have a situation like this. We have a volume, the initial pressure, and the quality, and we're told it's water. Of course, that's in this case, you can see it's going to be a water steam mixture. And so let's get an idea where we're starting and where we're going to end. So first of all, since we see that we have a quality here, we know we're somewhere inside this curve, inside this region here, don't we? So we can just maybe put a dot somewhere. So it's going to be our initial state. And I guess that's approximately, 3/4 across, maybe from here to here, about 3/4. And so, it's going to be the gas is going to be heated, the water is going to be heated until we end up with a saturated vapor. So first of all, since the volume is constant, we know we're only going to move vertically. We're only going to move up and down because here's the volume. If we were to go this way, that would mean the volume be changing, or this way, the volume be changing because the volume is on the x-axis. So we're going to have to be moving vertically, either upward or downward. But we're told in the problem that the final state is going to be a saturated vapor. And of course, this part of the curve over here indicates a saturated vapor. So we know we're going to go end up on this side of the curve. Remember, over here is saturated liquid, so we know we're going to be on this side of the curve. So somehow we're going to get from our starting point over to here. But once again, we know uh, we can't change the volume. So the only way to get from this state to saturated vapor is to go directly upward. So let's maybe draw a vertical line to show our second state. And that's our state two. So it's always good to start out trying to understand what we're doing, where we're starting, where we're ending. And so heat is going to be added. And again, like I said, we know that V1 is going to be equal to V2. And we also know we're going to use the first law. You can use probably either form. Maybe I'll start with Q minus W is a change in internal energy. So keep that in mind. And so we want to maybe write down our states. So it's state one. Again, we know we have a saturated mixture. And state two, we know we're going to be here, saturated vapor. And we know our initial pressure, our P1, is 650 kPa. And so we're going to have to look up some things. We're going to probably need, well, I guess it's clear we're going to need the internal energy, and we're going to need the initial volume. So let's look those up. So again, we know we have a saturated mixture. So we want to look in the saturated steam water table in whatever book you might have. Look that up and look up this pressure. Now, this particular table has the temperatures first. So we probably should go to a table that has the pressure first. And this is a table right here. In my book, it's table A11. And we want 650 kPa. So we're going to have to look up 650 kPa. It's not there. Down here is MPa. So under MPa, we're going to look at 650 MPa. And so that's going to be this line right here. We're going to look across here. And again, since we have saturated mixture, we you might as well write down all the values here. And so let's write these all down. So we went VF. So paused the video and just went ahead and wrote down all the values, the VF, VG, UF, UG, UFG on that same row on the 650 kPa or the 0.65 MPa, just went right across and did all these values. And then we want to actually calculate for state one. We know the quality, that's going to be our X value. So we're going to do V1 is going to be our VF, which is 0.01104 plus our 0.7335 times VG minus VF. Since these all have the same units, I won't write them down till I get the final answer. So we have this. And again, if you forgot how to calculate this, go back to the earlier video. I'll have it linked below, is to how to use the tables and how to get these values. So we have this, and when you put this on your calculator, this comes out to be 0.215 meters cubed per kilogram, like this. And I calculated the same thing for our internal energy. Did the VF times our quality times VG minus VF. And remember, in the internal energy table, it actually gives us this difference. So we don't have to actually subtract this from that. It's already given to us. And we get this. So let's go to state two. Now we think of state two, though, we're not given anything about state two except that it's a saturated vapor. So the only thing we can do then is use what we know. We know, though, V2 is equal to V1. And we know that V1 was down here. And that's all we know. We just know the specific volume, and we know that's a saturated vapor, of course, which means it's up here. So, so think to yourself, what do we have to look up to find the other properties? So if we know only this, and we know it's a saturated vapor, so that means saturated vapor, remember the subscript is like VG. So we have to look up in our table to see what pressure and temperature have VG equal to this value. So let's take a look in our table here. You could probably look up, we'll see the one that's closest. We can maybe look up at the temperature table or under the pressure table. Let's maybe look at both of them. So under the temperature table, we're looking for VG to be equal to 0.215 meters cubed per kilogram. And so let's just go down and VG 215, VG 215. This one's pretty close right here. 2168. That's really close. So that'll be maybe one of our candidates. So that was at 175 degrees C and 0.8920 MPa. But let's also check the pressure table. Let's go down the pressure table for 215. Oh, actually, look, interesting. The pressure table has it exactly. We can find 215 exactly there. So we could have used the other one because that was really close, but this is going to give us an exact value because VG is 215 here. This is at 175.38 is our temperature. Remember, the other one we had was 175, and this is 0.9 MPa. So from table, now in my book it's A11 if you're using the same textbook as me. This gives us our pressure, 0.9 MPa, and our temperature of 175.38 C. But let's think to ourselves, what do we actually need for that table? Now, if you look back up here, we're going to need the change in internal energy. And so we have U1, so we're going to have to find U2. So we know the row to look at, right? Because we found the row that had our VG at 0.215, then we can look there and find our internal energy. And once again, we want to use VG because we know it's a saturated vapor. So let's look across here. And this column, which is our UG column, says 225 80.5. Yes, we can write that value down. And so now we have everything we need to calculate uh, our Q. So let's do that at the bottom of the page here. Let me just make a line to separate these. So our Q minus W is going to be delta U. And so there's no work being done. Like it's just a closed system here, uh, rigid tank. There's no paddle wheel or anything in here. So therefore, the work is going to be 0. And so the Q is going to be equal to delta U. Now the delta U is going to be U2 minus U1. And since the units are the same, I won't. If you're working with something and both terms have the same units, we can sometimes save space by not writing them down because there's really nothing to check. But maybe I'll just kind of write it like this. And so when you put that in your calculator, you end up getting 513 kilojoules per kilogram, like that. Now we want that. So this is the heat added per kilogram, but we want to find the total heat added. So we're going to have to find the mass, aren't we? So we'll have to find the mass and multiply the mass times this value. And so we can find the mass by taking our volume is given, and dividing it by our specific volume. And I'll put V1, but it's actually not changing. Remember, V1 and V2 were exactly the same. And so this is going to be 1.2 meters cubed divided by our V1, which is 0.215 meters cubed per kilogram, like this. And when you put that in your calculator, you get 558 kilograms. And then, of course, if you want to find the total heat transfer, it's going to be the heat transfer per kilograms times the total number of kilograms. – 2863 kilojoules. Next, let's take a look at this problem. We have a rigid tank with a volume of 5 cubic feet, contains water at 500 degrees Fahrenheit and 200 psi. The tank is cooled until the pressure in the tank is 75 psi. What is the final temperature? What is the final quality? And how much heat was taken from the tank? So let's take a look at this. So again, we know we have a rigid tank. We don't have like the boundaries changing or anything. So that means once again, we're going to have V2 is going to be equal to V1 like this. Now, we don't know where we are in the TV diagram, so we're going to have to find out. Now, you can kind of suspect, since we're given the temperature and the pressure, we probably superheated, but we'll have to check in our table. So let's check 200 psi, see what the saturation temperature is at 200 psi. So in my book, it's table, let's see, where is it? Pressure is table B11, and look under 200 psi, and that would be this pressure right here. And notice that that pressure at 200 psi, the saturation temperature is 381.86 degrees Fahrenheit. But our temperature is 500. So we're above the saturation temperature. So this must be superheated. This. So we have to go to our superheated table. And again, in my book, uh, again, 200 psi. So in my book, it's table B11 for English units. And so we're going to look under 200 psi. And would we say 500 degrees Fahrenheit? That's going to be this row right here. And we're going to need the volume, and we're going to need the internal energy. And the volume is 2.724, and the internal energy is 1168. So let me write those down. Again, that was in my book, that's table B12. Again, you may have a different book. And again, the reason we want internal energy, remember, we're going to apply the first law. We're going to apply that Q minus W is going to give us a change in internal energy. This. But in any case, we determine our state when it was superheated. So we could be maybe somewhere out here. Let me just put that down for our first state, like this. And we're told that it's going to be cooled to a pressure of 75 psi. Now, again, we don't know where that's going to be on a TV diagram. The only thing we know is that the volume is not going to change. So that means that we're either going to go upward or downward vertically. So we're going to start here. We could go down maybe to here, 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 could be up here, but there's going to be a vertical change. So let me write down our second state was that our pressure was 75 psi. And again, the only thing we know is our volume doesn't change. We had a rigid tank, so that means V2 is going to equal to V1, which is going to be 2.724 cubic feet per pound. Now, to figure out what state we're in, we're going to have to look these up. So let's look up our pressure in the saturated mixture table. Or let's see, mine it's called saturated steam water. And we'll look up 75 psia, and we'll see if this value falls between VF and VG, or maybe it is VF or VG. So we're going to see if it's somewhere like in here. And of course, it's actually going to be, if it's in there somewhere, it's going to be like below, vertically below this. But let's look that up. 75 psi. Again, in my book, it's in table B11 and 75 psi. And this shows the volume. The VF is 0.017 and VG is 5.818. So our volume falls in between there. So we must have a saturated mixture. So we're going to be, I'm not sure exactly where it's going to be, but it's going to be somewhere down here. And I'll just put it somewhere in there. I just want to put it in the saturated mixture region like this. And so what are we going to need to find out? Again, it's between VF and VG. So we're going to have to find the quality, aren't we? So, of course, the quality will be our V2 minus our VF divided by VG minus VF. And once again, look it up in your table here. So that's going to be our VF is 0.017. Our VG is 5.818. And our V2. Again, since everything has the same units, I won't write the units down. Otherwise, but if one term has a different unit than the other, always write them down and be sure that things are canceling out properly. This, and when you put that in your calculator, you get 467. Now, once we know that, we can go ahead and find our U2 because we can use this for the U2. And again, for U2 will be our UF plus our UG, excuse me, our X, which is our quality, and our UG minus our UF. Of course, in our table, we'll be given that UFG, so we won't actually have to calculate the difference here. And we look at our table again at 75 psi. Our UF is 277.37, and the UFG is 824.3. Give us 662 BTUs per pound. Like this. That's, I believe, is all we're going to need because we're going to apply this equation. And again, you could convert all these to like just BTUs. You could multiply them by the mass right away, or you can do it later. It's up to you. I'll go ahead and calculate the small q and then multiply it by the mass. So again, we're going to have q minus w is equal to delta u. And again, there's no work, there's nothing going on inside, no paddle wheel or anything, and there's no boundary changing. So our Q then is going to be our difference in U, which is going to be U2 minus U1, which is going to be our 662 BTUs per pound, minus our 1168 BTUs per pound. And when I calculate that, that was negative 506 BTUs per pound. And that's going to be, again, the heat transfer per pound. Now, if we want the actual heat transfer, the BTUs, we have to find out what mass we have. Of course, again, the mass is going to be the volume divided by the specific volume. In our case, we had 5 cubic feet divided by our specific volume was 2.724 feet cubed per pound. And that's going to give us 1.8355 pounds. And finally, to find the heat transfer, we're going to take our Q times our mass, which is going to be our minus 506 BTUs per pound times our 1.8. I'll use all of this, but I don't have room to write them all in here. And so it's 1.8 pounds. And when you calculate 1.8355 pounds, we multiply that up, I get 929 BTUs. Of course, that's work, it's heat removed, of course, since it's negative. And there you have it.